My thesis is on designing and evaluating a general aviation primary flight display with main emphasis on human factors. All this research was done at RISE and MIMS lab under the guidance of Dr. Jung Chang, who was very helpful and supportive throughout these years. This will be the agenda of this presentation, where we will discuss about the overview, followed by the problem statement, and the design, the testing and the results, and then the conclusion and future work. To provide a brief overview of the project, this research focuses on reducing human errors made by general aviation pilots that potentially affect the safety of flight, causing fatal and non-fatal accidents. In order to do that, a human-centered design approach was chosen to design a new primary flight display to increase situational awareness and also to reduce pilot workload. And once the new primary flight display is designed, pilots were invited to test the new design against existing aircraft displays, and the feedback was recorded. And based on their feedback and also the flight test results, suitable conclusions were drawn to improve the design, and all the shortcomings were addressed. Based on the literature review conducted from the year 2008 to 2018, on average, each year, close to 1,200 accidents occurred during landing, and close to 500 accidents occurred during approach. And mainly, during landing and approach, accidents tend to occur more frequently when compared to other phases of flight. And mainly private airplanes or smaller airplanes get into accidents when compared to other airliners and air companies. And a report published by National Transport Safety Board also revealed that controlled flight into terrain, loss of control, and power loss are the top three reasons for most of the accidents occurring in the general aviation sector. Hence, this forms the objective of this thesis, which is to reduce accidents in general aviation aircrafts, mainly due to CFIT and loss of control incidents. Human factor studies conducted by NASA also revealed that skill-based and decision-based errors account for more than 80% of the total accidents that occur due to human error. And even though factors like situational awareness, aeronautical decision-making, risk management, and automation play a major role in the safety of general aviation, pilots, human factors play a crucial role, and all the other factors are dependent on human factors as well. Similar studies conducted by NASA showed that human factor analysis and classification system could be used to analyze and classify all the accidents, so that that data could be used to prevent further accidents from happening. It's based on the Swiss cheese model of human error that states that human error could be divided into 4 different levels, where the last 2 levels, which are preconditions for unsafe acts and unsafe acts, are the main levels where a pilot could do an error which could snowball itself and lead to a fatal accident towards the end of the model. And these are some of the reasons due to which pilot tends to get involved in fatal and non-fatal accidents due to negligence of weather, altitude, terrain, inadequate training, and disregarding checklists. All these errors would be crucial to propose a solution or to design a new primary flight display symbology, which will be discussed in subsequent section. So the first step in designing a symbology is to get a theoretical understanding or to understand the basis of creating a symbology design. And in order to do that, FAA handbooks, advisory circulars for electronic flight display designs were consulted in order to design a theoretical design of the symbology. And there are several factors that affect the symbology of the design, namely sizing, position, color coding, labels, and dynamic information. And all these factors play a major role in designing a proper symbology that will communicate to the pilot the current condition of the aircraft, which will be crucial to reduce or to avoid accidents from happening. And based on each iteration of the symbology design, pilots were consulted, and based on the feedback, every iteration of the design was improved in order to get to a final display symbology design. And as discussed earlier, one of the methods of designing a symbology was applying a task analysis, which is commonly used in civil aviation design, also known as hierarchical task analysis. This method was chosen because it breaks down major objectives into subdivisions and it develops products to satisfy all these conditions, which in our particular case, in order to design a symbology, we need to break down objectives in order to solve in order to avoid accidents from happening as per the objective at hand. So understanding all the errors that we have, we will apply the hierarchical task analysis to all these errors and propose a solution that would solve or that could avoid the error from happening. In specific to this thesis, applying hierarchical task analysis to the CFIT accidents, this are nothing but control flight interterrain accidents. All these three are some of the conditions due to which pilots tend to get involved in CFIT, which are altitude or airspeed negligence, less situational awareness, and flying VFR and IMC. And in order to solve these three conditions, a pilot should have information of all the primary flight instruments. And apart from that, he needs to have an angle of attack as well as an instrument and landing system. And the pilot should be properly trained in order to face unforeseen circumstances. To avoid such CFIT accidents, providing three-dimensional waypoints to the pilot within the symbology could help the pilot to visually guide the aircraft throughout the flight path and to land the aircraft safely. And applying terrain textures to the digital elevation models would also be helpful as per the literature review conducted earlier. And based on all these criteria, some of the basic key points that I noted are mentioned. And based on this, the basic primary flight display symbology was put forth. This figure shows a basic primary flight display symbology, which was designed based on hierarchical task analysis, as well as human factor studies conducted earlier. And this symbology has all the basic flight instruments that the pilot need to take off, cruise, and land the aircraft safely. And apart from that, this symbology also has instrument landing system inbuilt in it, which would be helpful to the pilot during low visibility conditions or bad meteorological conditions. Adding to the basic primary flight display symbology, a series of three-dimensional waypoints would be added along the flight path to visually guide the pilot throughout the flight phase. And what this does is this helps reducing the pilot's workload. So the pilot would just have to fly the aircraft within the designated three-dimensional waypoints. And this helps considerably reduce the mental and physical workload imposed on the pilots, especially during difficult flight phases like landing or takeoff. And this method has been proved effective as per literature. And the shape and the color of the three-dimensional waypoints are crucial. And for this thesis, pilots' feedback and literature review data was used to select the final design and color of the three-dimensional waypoints. And each waypoint was situated as a fixed location from the ground after the latitude and longitude of each waypoint was calculated. And in addition to the waypoints, terrain textures were added to the digital elevation models. And this helps in visualizing the peaks and valleys of the terrain, which could help the pilot, especially during low altitude flying conditions. And the pilot needs to maneuver on top of mountains or any other object. And there were 4 different textures that were currently used for the thesis, where the final one, the hexagonal grid texture, provided better results since that was finally used throughout the flight model. So the digital elevation model used for this project was the Aden International Airport, situated in the city of Yemen. This was a local terrain used throughout the flight test. And the pictures shown here show a sample of the digital elevation model used, which is superimposed on top of the symbology. And in order to reduce computational requirements, man-made elements like buildings, roads, and trees were stripped from the terrain. And this also helped in reducing computational lag, and which increased computer performance. Hence, the final display symbology, also known as the combined vision display system, incorporates all the key elements of a basic primary flight display symbology, terrain textures, digital elevation model, and three-dimensional waypoints. A combination of all these instruments help the pilot to better visualize the outside terrain without even having to look outside the aircraft. And this becomes helpful, especially during low visibility or bad meteorological conditions. So the software resources used for this project were supplied from Presages, which has all the in-house software used to design, develop, and implement a complete flight simulation model. So Presages Flight Sim was used for flight simulation and for developing the flight model, and WAP60 was used to design the primary flight display, the PFD Symbology, and the Presages Vega Prime was used to deploy and visualize the digital elevation model, as well as apply the terrain textures on top of it. And another in-house program called NCOM, provided by Presages, helped to transfer data between all these programs so that data could be easily transferred between computers at a rapid pace. And especially for this project, two computers were run simultaneously at the same time, and the data was transferred between them in order to reduce computational requirements as well as to reduce the lag. And as discussed earlier, fixed base flight simulator was used as a testing medium for all the flight tests. And as discussed in the previous slide, two computers would be used at the same time, where one computer would be used to display the out of the window view, and the second computer would be used to display the primary flight display symbology. And in order to simulate actual flight conditions, flight controllers, high fidelity flight controllers, were used in order to control the aircraft for pitch, roll, and yaw conditions. And in order to compare the newly developed combined vision display system, two existing aircraft displays called analog and digital display system were used and tested in conjunction with each other so that it could help to serve as a benchmark, and it will also help to compare the advantages or disadvantages of new display over existing aircraft displays, and this will help us to improve the design in case of any shortcomings. All the displays had all the basic primary flight instruments the pilot need to take off, land, and cruise, but the CVDS display had the terrain textures which were not available in the other two displays. Prior to beginning the flight test, Ryerson Ethics Board approval was used since this research involved human flight testing, and a total of 10 participants were invited, and most of them were pilots, general aviation pilots with PPL licenses, and the other participants were simulator pilots with considerable amount of simulator experience. All the participants were encouraged to follow the requested flight path, and the total simulation time lasted for about 500 to 600 seconds. And they were asked to simulate a normal takeoff, cruise, and perform a normal landing. And there were no gust winds, and the normal weather conditions prevailed throughout the flight simulation. And this graph shows a consolidated flight test results of all the participants using an analog display. And it can be clearly seen that the participants were not able to follow the desired track as requested, and there was a high range of deviation from the desired track. And this shows that participant had difficulty in following the desired track, and the results had a high range of deviation. Similar results were also obtained by participants using digital displays, where they had difficulty in following the desired track. But when compared to analog display, participants were able to follow the desired track close enough, in contrary to analog display. Participants using combined vision display systems found it easy to follow the desired track because of the availability of three-dimensional waypoints, apart from one participant that deviated from the desired flight track due to some difficulty in following the waypoints. And this goes to prove that the availability of three-dimensional waypoints helps the pilot to follow the desired track and land the aircraft properly. And in order to better understand the results, all the participants' performances were averaged per display, as it can be seen from the graph shown here, where the averaged track of analog and digital display had a high range of deviation from the desired track, which was not observed in the case of CVDS track, which was close to the desired track, which also implies that participants were able to follow the desired track closely. And in order to represent the results in a different way, a slope of the landing profile of each participant was calculated and compared with the slope of other displays so that it could help us to understand the range of fluctuations at which the participants land at the aircraft. And it can be clearly seen that participants using analog and digital display had a high range of landing profile fluctuations that ranged between 0.2 to 1, which was higher than the requested range of 0.7. But participants using CVDS displays were able to maintain a constant rate of landing profiles close to 0.7, which was exactly the same or close to 0.7, which was the requested value of the desired track. And using statistical analysis in order to compare the results, it can be clearly seen that the mean deviation of analog and digital displays were high when compared to CVDS, which is also expressed in terms of tracking error and standard deviation, which also shows us the same results. So the CVDS display performed better in terms of performance, and participants were able to land the aircraft properly, and the tracking error was also considerably less while using CVDS in comparison to analog and digital displays. Comparing the touchdown points of all the participants using the three displays shows that participants using analog and digital display had difficulty in landing within the safe landing zone, while participants using CVDS displays were able to considerably land within the safe landing zone or close to the safe landing zone as seen from the figure. And also the standard deviation range of analog and digital displays were comparatively high, which was not observed in the case of a CVDS displays, because the standard deviation ring exactly coincided with the safe landing zone, which goes to prove that participants were able to land within the safe landing zone following the three-dimensional waypoints. After each flight test, participants were asked to fill a non-intrusive survey report of a NASA TLX form and a Bedford workload scale form, which helps us to gauge the participants' performance in order to understand the mental, physical, the temporal demand, the amount of effort and performance exhibited, the amount of frustration that the pilots felt. And the Bedford workload scale gauge the participants' workload and to check the amount of additional workload capacity that the participants had in addition to completing the flight simulation task. And the results were graphically plotted as shown from the figure. And it can be clearly seen that participants using analog and digital display had high mental, physical, and temporal demand, and the performance was less, and the amount of effort and frustration that they had and they felt was high when compared to CVDS displays. But on the other hand, participants using CVDS display had less physical, mental, and temporal demand, and they were able to perform better, and their effort needed to fly the flight model by using the three-dimensional waypoints and terrain textures improved their performance while reducing the effort needed for control, and they also had reduced frustration levels. And the Bedford rating also revealed that they had additional mental capacity to spare, which was not observed in case of analog and digital displays, that showed that participants had experienced higher workload conditions. Based on all these results, we could come to a conclusion that the CVDS display performed better when compared to other displays, which shows that participants had less mental and physical workload, and they had high situational awareness as well as task awareness, which would be crucial to reduce accidents in case of a real scenario. And this method could also be used to add a traffic collision and avoidance system within the CVDS display, so that the pilots do not have to look outside. They can completely rely within the CVDS display for all the information, and this would be helpful during low visibility conditions when they have to completely rely on primary flight instruments. The synthetic vision techniques, the main disadvantage of synthetic vision techniques is clutter and information workload. And CVDS display is an improvement over the current synthetic vision techniques. And this proof of concept provided within the thesis shows that even though synthetic vision techniques were employed within this thesis, the CVDS display reduces the clutter and provides helpful guidance for the pilot during landing and approach, which could be pretty beneficial to avoid CFIT and loss of control accidents. And in terms of future work, the proof of concept shown in this thesis could be applied to personal aerial vehicles, which is increasing demand nowadays. And researchers are working to automate or to transport people from one point to another to avoid traffic congestions. And common people without any flight experience would be able to fly the aircrafts by using this technology with minimal guidance. And provided the current pandemic situations, drone delivery systems could be used to deliver non-essential and essential goods locally, and this method could be employed to control drone deliveries throughout the world. And based on the results of this research and findings, they have been submitted to the Journal of the Human Factors and Economic Society Journal, and we are awaiting scholarly review. And the next step would be publishing this information within the journal. Once again, I would like to thank all the committee members for agreeing to be a part of my oral examinations, and thank you so much.